We introduce spherical cubic blends, our method to interpolate rotations. Our motivation is that we want to compute the trajectory for our robot's end effector as shown in this video. Thereby, we want to interpolate several given rotational waypoints. Last ICRA, we proposed a method to interpolate waypoints in configuration space. For task space planning, we can reuse this method only for translational waypoints, because these are also part of a Euclidean space. Rotational waypoints, however, are not. Rotations are part of a nonlinear space, in which interpolation is more complex. However, there is a corresponding linear space, and there are functions to transform rotations between these two spaces. In our approach, we transform rotations to the linear vector space. Therein, we interpolate. Afterwards, we transform the result back into the nonlinear space to get the interpolated rotations. The nonlinear space of rotations is the special orthogonal group of 3 dimensions, short SO3. This is a Lie group. To work with elements of that group, we need to define a representation, for example, rotation matrices. The choice depends on the application. In robotics, we need to concatenate transformations a lot. That is, we need to compose 2 rotations to compute a new rotation. For this composition, unit quaternions are computationally efficient, and therefore we represent rotations with unit quaternions. The corresponding linear vector space of this Lie group is the Lie algebra, in which we want to interpolate. The Lie algebra uses 3 parameters to represent rotations, and we refer to it as scaled axis angle representation. That is, we define an axis of rotation and scale this axis by the magnitude of the angle. To transform an element from the Lie group to the Lie algebra, we use the logarithmic map. For the representation with unit quaternions, this slide shows the 2 formula how to compute the scaled axis angle representation given the 4 parameters of the quaternion. Phi is the angle and omega denotes the axis. To convert an element vice versa, that is to say, to compute a unit quaternion given the scaled axis angle representation, we use the inverse, that is the exponential map. Our contribution is a method to interpolate rotations with the approach just shown. Our requirements are, first, we want a C2 continuous trajectory profile. That is, we want to have continuous accelerations so that only minor vibrations result. Second, we want a trajectory that is zero clamped. That is, the desired velocity and acceleration at start and goal has to be 0. Third, we want to exploit the actuator limits so that we traverse the waypoints at high speed. 4, we want low computation time so that we can compute the trajectory online. Our interpolation idea is derived from the parabolic blends approach that was proposed for configuration space. Translating this idea to rotations means that we want to move with maximum angular velocity in between 2 adjacent waypoints. This is indicated by the orange lines on the right picture. And we want to blend these velocities around the waypoints with maximum angular jerk. This is indicated by the blue lines that show acceleration and deceleration phases around the waypoints. So our interpolation has 2 phases, phases with constant maximum angular velocity and phases with constant maximum angular jerk. There are 2 steps for the computation of the trajectory, an offline and an online step. This slide shows the offline computation step that computes the interpolation. The formula of this algorithm are not important, and I refer to our paper for the mathematical details. Highlighted in orange, however, are the steps that compute the linear motion phases with constant maximum angular velocity and blending phases with constant angular jerk. Further, there's an iterative optimization of the durations in between the waypoints. That is, to exploit the actuator limits, we iteratively extend or shorten the duration of the motion segments. Note that we also decrease the maximum jerk if the maximum acceleration would be violated during blending. This diagram shows from top to bottom the trajectory profiles of the quaternion, the angular velocity, the angular acceleration, and the angular jerk. One can see the linear phases in which we exploit the maximum angular velocity of 2 radians per second, and the phases in which we move with constant jerk, that is linear acceleration at its limits of 220 radians per second squared. The offline computation step interpolates in the linear space we have seen earlier. The second step, the online evaluation step, evaluates the trajectory and thereby computes the exponential map. That is, It computes the unit quaternions at any time from the interpolation in the linear space. I refer to our paper for details. In experiments, we benchmarked our proposed method with similar approaches. This diagram shows the trajectory profiles and our SCB method in dark blue and its absolute values in light blue. All methods interpolated the same rotational waypoints. Our method meets the defined requirements. We have zero clamped boundaries at start and goal. We exploit the actuator limits, that is, the angular velocity is at its limits during the linear motion phases, and the angular acceleration is at its limits during the blending phases. Further, the trajectory is C2 continuous, that is, there are no discontinuities in the acceleration profile. Finally, this table shows that our SCB method has the lowest computation time of 88 milliseconds for the given scenario. We provide references on this slide, and thank you for your attention.